Well, let's talk about the concept of diffraction and refraction and Snell's law and see how that relates to sound and how it relates to light waves and so on. There's this interesting experiment, and you don't see it too many physics classes now, but very common old school thing. And you don't necessarily have to draw this, but there's this big water table. Excuse me. So here's a water table, and underneath this water table is a light bulb here. So there's a light source underneath. And on the one end of this water table, right, there's water in this skinny table, right? You have a little wave generator. That's literally what it's called. So there's a little motor that hangs off the end. Okay, we'll give him a plug too. And on this wave generator, you get this consistent pattern of waves, right? So it sends these waves out. They're propagating that way, right? They're moving forward, which makes sense. Okay, you could actually do this with your hand. And then you can take bricks, solid, unmovable bricks, and you put another one over here. And what happens, though, afterwards is really cool. Now, you would say, well, okay, then I'm going to get this, right? But you don't. You don't. That doesn't happen. So let's going to get rid of that, right? That does not happen. That situation there, no. Okay, so what does happen? Let's take a bird's eye view of this, and we'll turn it more like that. And this time we're going to certainly draw the block of wood, right? So there's a block of wood here and his little motor. Okay. And the bricks are still in place. And I would hope that you agree that water moving in a table certainly is not going to move bricks. Okay, but we have these waves here. And you get this. Now, that hardly seems to make sense, but that's the idea of a phenomenon, right? It's unexplained. It doesn't seem to make sense. So what's going on here? Well, first of all, that concept is called diffraction, and it is a spreading of waves through an opening, right? The spreading Now, what's interesting about that is that the opening has to be similar in size to the wavelength. Okay? So, opening is similar in size. And this is true for sound and light. Now, how do I know what the wavelengths are? Well, that little light underneath here, right? These lines here, actually, they do look like lines, and those are actually the peaks of the waves, right? So you could draw that, right? It's just the way the light shows. So it must be that the light gets deflected or refracted. We'll learn about that later on. But they look like lines. They're very steady here. But here's the other part is, why is this happening? Where is this origin, right? So what's going on there? Well, that's a phenomenon, and you can look into that later, but that's what happens. And you also get this curved shape. Okay, there's some other mysteries that go on with this later on, but that's the general idea. That's diffraction of water waves. Now, this will also happen with light, but I want to show you what happens with sound. Okay, this concept of diffraction with sound. All right, so back when we had a classroom, not that I'm bitter, okay, but back when we had a classroom, right? Here's the opening to the classroom in the physics room, and so here's the door on the edge, and there's little hinges, okay? On the other side of the hallway were the lockers. We fondly remember our old lockers. Okay? Each of them has a vent. Okay? So one of your buddies is hiding out on the side of the door. They just miss you so much that they can't be without you. So they're on the other side of this door. Okay, that's your friend. And we could say there's a friend over here. Okay? Benway's talking the whole time about physics, right? Blah, blah, blah. Physics is exciting and okay. So blah, blah, blah. And when I talk, really, I'm compressing the air, and then there's a rarefaction, and so, okay? But we really could represent it like sound waves like that, okay? We could use transverse waves. So I talk, and the sound goes out into the hallway, right? And your friend later tells you after school, because they're so excited to tell you about all the physics that they also learned, that they said, I could hear Benway. And you'd say, well, of course you heard Benway, right? The sound bounced off of the locker and came back to you, right? Or the sound bounced off of here and eventually made its way to your other friend. But, okay, let's get rid of those lockers, which we did. Again, I'm not bitter, all right? So we have this door. We now got rid of the lockers, and let's get rid of the wall, right? Let's get rid of all of that. Your friend's still here, and his or her twin. Doesn't matter. How can we still hear that? Because they're going to report to you that, yes, they still heard it. Okay, so now let's take this door here and thicken the walls, I guess, right? How are they still hearing it? Well, that's why diffraction is a phenomenon. The sound waves come from me, talk, right? All of these. These are similar in size to this opening here, right? As it goes through, though, you get that diffraction pattern. And so people on the other side, even though there are no lockers to reflect the sound, that's what happens. So that's the craziness of diffraction. So that is one of the light phenomena. Wave phenomenon is diffraction, is the spreading out of a wave through a small opening. All right, so we should talk about another type of light behavior. Let's start a new page. And this one is refraction. And we've seen this before in with prisms or with the spectroscopy lab when you do that in chemistry, where you have the little black tubes that you look at the gas lamps. Okay, so refraction is this crazy concept here. One of the stories that I have heard is that there's this large vase. I saw this in a story. I don't care if it's true or not. It's a good story. All right, and so this is filled with water. And this is about Galileo, right? Galileo Galilei. He's the only scientist that we call by his first name. How cool. Okay, we call him Einstein. We don't call him Albert, but for Galileo, hey, we go with his first name. So here's the water, and there was something on the other side, a person, a book, whatever they had. But he could tell that it was upside down. It was inverted. And he said, what in the world's that? So he, made a career out of doing that and making lenses and all that stuff. So the idea is that he knew that he looked through this, but because there was a rounded shape, right? If we look on top here, there's a rounded shape here. There's a shape, a source, an object on the other side. And for some reason, when it came through, it was inverted. It wasn't just upside down. The sides were also back and forth. Okay, what in the world is going on here? All right, well, we could keep this picture going. And it turns out that, let's say there's a coin here on the bottom of that water. Okay, on the bottom of that surface here. And water leaves here right? Water's going to leave, the light wave's going to come from this, right? Somehow light strikes that in the water, and then the light wave bounces off of the penny, right, and goes to the surface. And we're going to see something very interesting that happens here, okay? What happens when this wave goes into the water, okay? Does this happen? Does it go this way? Does it go that way? What happens? Well, that's where we are, folks. We're going to talk about the concept of refraction. Now, all right. In college, they're probably not going to like this. Bending, light waves don't bend. Okay, yeah, but they kind of do. No, they don't. Okay, they kind of do. So it's kind of like saying heat rises. Well, he doesn't really rise. He's pushed up by more buoyant fluids underneath, but heat rises, you know. And so that's the same idea here. Refraction kind of is the bending of light, but we'll get more into that later. So how do we set this experiment up? Because we're actually going to have a virtual lab on this, okay? And it's a really cool situation here. But before we get into that, before we do the pre-lab, we should talk about speed of light. And the speed of light has its own symbol, the letter C. I have no idea why. But it is said to be pretty much 3 times 10 to the 8th meters per second in a vacuum. Now, if we really go with the actual number, this is really something like 2.9898 or something. Hey, we're going with this, okay? 3 times 10 to the 8th meters per second in a vacuum, but that's not the speed of light when it goes through water or goes through glass. So it's different, right? So here, the speed of light. Okay, but if we consider some of the media, for example, water, glass, plastic, they don't do that. They have a different speed of light. Actually, it slows down. Okay, it slows the light down. Now we could talk about air. Air pretty much is vacuum. Okay, as far as we're concerned, air and vacuum, it's the same speed of light, indistinguishable by us for sure. All right, so these things we need to know. So what we do is we set up this ratio. Now later on you're going to see that this is called the index of refraction, and it's going to be something very useful. All right, so the letter N, what does that mean? Well, I know that the speed of light is always going to be faster than anything else, right? The speed of light is always going to be faster than whether it's in water or glass or so on, okay? So what we're going to do is put the speed of light here above the velocity in any other medium. Let's make it singular, okay? This is something you should know. So the speed of light is always greater than any medium. And so we could say, if I had the speed of light, 3 times 10 to the 8th meters per second, well, we could go with glass. And glass, probably, it's not wrong to say it's 2 times 10 to the 8th meters per second. Well, that's pretty easy math. That's just an index of refraction of 1.5. Okay, now we could say its tendency to bend light, right? I mean, we could. The tendency to bend light. Okay. And diamond is even greater. Diamond gets us to like a 2.4 or something. Water's like a 1.3 or something. I'm not sure, but the idea is that the speed of light here has a value associated to the medium that it's in. So there's this index of refraction. Okay? But we should look more closely then at just how this works. Okay? We could probably just let's just do that. We're going to take a piece of glass, and we'll draw it as blue, I guess. So we'll have a sheet of paper here. We're going to lay this on the tabletop. Okay? And on this piece of paper, we're going to take this piece of glass or very thick plastic, for example. Okay, so there's the glass. And what we do is we are going to view something through this glass, right? We're going to look through this long edge in there. I don't want that arrow to complicate things. So what we do is we take a pen, we draw this thick line on one side of that. Okay? And then what happens is we view from this side, right? So we're going to view from here, so we're going to get down to the tabletop level, right? And we're going to look through this edge, and we're going to draw what we see, right? And so we do see there's another line there. But here's where it gets really interesting, right? So this is the way we draw eyeballs in physics. And so what happens? We take this sheet of paper now, and this time I'm going to draw it another bird's eye view. Okay, so let's take our diagram here, and this is going to be the outside edge of the block of glass or plastic. So I'm going to draw that blue in there just to kind of remind you that that's what we had, was just a block of wood or block of plastic. Okay, and I'm going to draw this in red now. I drew this red line, let's say, on the other side, and you were over here looking through the glass, and as creepy as it looks, right, there's your eye. That's how we draw it in physics, right? So your eye is looking at that. And you, hang on, now I have to draw this. Yeah, so you get this situation here, right? We should have put your eye in the other place, but that's really what it looks like from the top. And you say, whoa, 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 whoa. It went through glass. What's going on? Well, that's the idea. So here's what happens. You remove this plate, and you draw this perpendicular right there. That's called a normal, right? A normal is just another word for perpendicular. Okay? And we can draw another normal here. Normal. Small case. And we would expect, we would think that, okay, the light's going to travel through like that. And it doesn't. It actually bends. It refracts. Don't say bend in college. They'll probably get all upset. Okay? I'm going to change this to green. But you get this. It actually changes direction. That you can say. It changes direction. Now what's going on? Well, there's a reason it happens, and we can show you later. It has to happen at an angle, so this incoming light has to be at an angle, right? But let's now look at this. This angle we call theta or theta. Not really theta, but that's called the incident angle, right? It is incoming. It caused incident, right? That's the incident angle. And then this guy here, this is what we call the refracted angle. It's the one on the inside, so it is with respect to the normal, right? So theta r is a refracted, right? That's a refracted angle, if you will. And so what happens is when the light comes back out, it turns out these two are parallel, That's crazy too, right? If this is a 180, right, and this 180, these guys are parallel, for example, right? Even if you tilt this, so if you were to have this incoming light at such and such an angle, right, then this other guy would come out there too, and it would be parallel. So that's the concept of refraction. It's really strange, but we do have some equations that go with it before we get to a lab situation. So those are just the concepts of diffraction and refraction. Let's make sure we got it. Let's go back through. And diffraction is the concept of the spreading of light waves through a small opening. The idea is that the incoming waves should be similar in size to the opening, and then the waves passing through should still be the same wavelength, although it doesn't quite look like that. Okay? The way we used to do it in old school is that we'd have water waves, okay, but they don't come out parallel like this, linear. They come out parallel curved, okay? So it worked with sound too. If somebody's speaking in a room and somebody's on the other side of the wall, they can say, "I still heard you," and you might say, well, that's because it reflected off of the lockers. But if we remove those lockers, they can still say, "I heard you," because diffraction happens through small openings. Now, this opening here is similar in size to the wavelength between the sound waves. Sound waves are about 1 meter apart. That's 1 meter in wavelength. Okay, we did that with the sound tubes. Okay, and so this is similar enough, and you get diffraction there. Okay, the other concept is called refraction. Now, somebody, and Galileo we suspect was the first one because he studied lenses, was he realized that a circular container of water inverted shapes. Now, we haven't talked about why that happened, but it led him to study light as it traveled through water or other things. We didn't have plastic back then. And so it turns out he didn't know this, but he was close enough. The speed of light was the fastest thing, but it slowed down. Now, he didn't know that either, but we now know that there's this thing called the index of refraction. We've known this for a very long time. The speed of light is faster than the light in any other media. So light in a vacuum, that fast. Light in anything else, slower. So the index of refraction is always going to be greater than 1, right? Because nothing's going to be bigger than that. Okay. Later on, what we're going to do is a lab called the index of refraction using something called Snell's law. And it shows us that when light travels through an object, it actually changes directions. We don't really say bend, okay? But the idea is that incoming light, we can see that, right? A pencil line reflects light, we can see it, so it's light. It comes through the glass, we would expect it to go straight on its path, but instead it changes directions, and then it emerges parallel to what it was in the first place. But these two inside angles here are going to be very relevant for a lab that we're going to do later on.